just looking around in 2005, 2006 at the number of people applying to study computer science, and just this sudden horrible realization that we'd driven off a cliff, and kind of like Wile E. Coyote, we'd gone off a cliff, and then we looked down, and yeah, we're in real trouble. So yeah, it was just trying to eke our way back towards that 1980s world in which every child who wanted to be a computer programmer had a machine that they could use to learn on. Then there was this period of 3 or 4 years, 5 years, where we were just kind of grinding through, iterating different processor architecture choices, different vendors. So we started off with something that actually looked a lot like an Arduino. Turns out you can take one of those, we wanted it to be a real computer, we wanted it to be a computer with a user interface, and it turns out you can take those microcontrollers that are in the Arduino, and you can make them generate a video signal. If you clock them hard enough and you write the right software for them, you can make them generate a component video, a standard definition component video signal. And so we started off, I still have it, it's a piece of Veroboard, which is about that sort of size, which has an Atmel chip on it and a block of SRAM, and it gives you actually a very kind of a 1980s computer experience. And the lovely thing about it is, because they're all 0.1 inch through hole components, you can build it yourself. You can build it it takes about an afternoon, a rainy afternoon. You can go in with a piece of Veroboard and some chips and come out with a computer. And that seemed like a really nice idea, but when you take it and you show it to children, what you find is that they're not really, it's not exciting. It's not contemporary, it's not modern. Those computers we got in the 1980s, we didn't necessarily get them to learn to program on. We got them to play games on, we got them to do other things with, and they just wheedled their way into our lives, right? They snuck into our lives, and once they were in our lives, then we learned to program. We didn't necessarily get them, And so really, I think probably most of that 5-year journey was about seeing if we could reconcile the idea of a $25 computer with a feature set that would make it attractive to a modern child. And another thing we found with all of these, and with that and with some subsequent architectures we tried, what we found, all of which were based on kind of very special purpose pieces of hardware. What we found was we were having to do everything ourselves. So we were writing our own SD card drivers and our own terminal software and our own keyboard drivers, and you end up doing an enormous amount of work because you've chosen to you've cheaped out on some aspect of the hardware. You're using some wacky DSP as your processor. You're writing this giant software stack yourself, and it was only really at the point where we got into a point where we put an ARM. We were lucky enough. So my day job for most of that period has been working for a company called Broadcom, who are a big fabulous semiconductor company. We make chips for communications. Pretty much every communications application has a Broadcom chip, we were looking at a range. We took the Raspberry Pi concept through a series of Broadcom chips, seeing whether we could get something compelling, and we were very lucky that towards the end of that period, one of these chips ended up with an ARM in it, and so we made that leap from this special purpose world with us doing all the work into a very general purpose world where really what we're making is an ARM Linux box. And so we're a not-for-profit. Our funding came from a couple of us throwing money in a hat. Quite a lot of money in a hat, but it was quite a big hat. But it was that seemed appropriate. But the thing that was really surprising to us after we announced in 2011, after it kind of almost leaked out, it was just a kind of a slip of the tongue. We didn't suddenly we were surprised by the level of interest. It became apparent to us that we really weren't going to be able to manufacture these. We weren't going to be able to manufacture them in anything like the numbers that were going to be required to suit the demand. And that's why you kind of see us, if you go look back at our website, you see us in 2011 talking a lot about manufacturing. And then towards the end of 2011, start 2012, our entire business changes. So we become a licensing company. So what we are now is this very capital light licensing company. We design this, we work on the brand, we work on the software, we work on the hardware, but all of the manufacturing and the capital provision and the logistics, they're all provided for us by our partners. And we have a couple of partners, RS Components and Premier Farnell, who are kind of multi-billion-dollar electronic component distributors, and that's really the thing that's let us go to scale. The really wonderful thing is that we were able, in terms of who does the manufacturing, like everyone else, they don't manufacture, they commission manufacturing from a third party, from a CEM. The wonderful thing for us was that last year we were able to move our manufacturing back. So we started building, like everyone else, when you say, I'm going to build something cheap, where I'm going to build it in China. And over the course of the last year, we've steadily reshored manufacturing of these things to a point where now 100% of these are being built in South Wales. Right, so they're being built in the UK. So that level of support, having these kind of big UK PLCs on site, has given us the kind of level of volume and the level of support that we've needed in order to really make that happen.
What is really on this little middle chip? But that's like a whole, that's pretty much it, right?
That's pretty much it. And really you can see the Raspberry Pi almost as being a breakout board for that chip. So this chip's called BCM2835. It was designed here in Cambridge. It was designed by the team that I'm a member of, just about 2 miles away from here. It was originally intended as a coprocessor. It's intended as a multimedia coprocessor for a mobile phone. So if you've got a mobile phone platform that's performing well, but maybe it's halfway through its life, and you want to give it a bit of a shot in the arm and bring it up to particularly maybe 5 years ago, where we were moving from a world of really fairly simple mobile phones to a world in which every mobile phone is expected to have video playback and good camera processing and 3D graphics, that this could be used as a shot in the arm processor to allow you to bring an older platform up into the modern era. And then the last one of them grew an ARM. So this thing already had most of the other stuff you need. It could drive an HDMI display, could drive a standard definition display, it had a 3D accelerator and a video accelerator and a camera processor and some DSP and a USB controller, which was kind of an unusual feature to have in there. And really what we found was that looking at this chip, man, we're only an ARM away. We're only an ARM core away from this being a computer, a single chip computer. So we were lucky enough to be able to get an ARM core into the last stepping of 2835, the final production step, grew an ARM 11. And that's what allows us to run Linux. The really interesting thing has been that a lot of what people have done with this has been hardware hacking. We have these GPIOs here, which for me kind of a little bit of an afterthought in the design, but in practice a lot of the cool stuff people have been doing, adults and children, have been about using this as a machine. Because you ask, is this just a cheap PC? What can this do that a PC can't do? And in a lot of ways it is just a cheap PC, but this stuff is something that your most expensive PC can't do without an add-on card. And so people have been taking these, they've been putting them in boats, and they've been putting them in planes, and they've been putting them under balloons and sending them up to the edge of space, and they've been using them to automate their homes. There's a wonderful example someone had the other day of an augmented microwave. He'd taken an old microwave and completely overhauled the user experience of using this microwave. So it had a new touch panel on, it had voice commands, it had a web interface so you can control it from your iPad, it had a barcode scanner so you could scan the product, and he'd built a database that mapped barcodes to cooking instructions, so you could just scan it, put it in, and it would cook it for you. And he built this thing with a Raspberry Pi. It's given people access to a kind of a level of technology. It's given people access to a platform that they can use to do all this really amazing stuff. And so it's wonderful because a lot of the people doing this are adults, right? But the lovely thing is, a lot of these things adults are doing with it feed immediately into the range of projects that are available for teachers. We take this and we take it into schools, and at the end of the lessons, mixed ability classes, at the end of the lessons, there's always a hardcore of kids, boys and girls, who you have to basically prise the thing out of their hands. Because, particularly if it's their first experience of programming, and even if they've done something very simple, like we often use a snake game. Even if they've done very simple stuff like change the color of the snake or make the snake go a little bit faster, that kind of power, you can see it in their eyes, that they're like, hang on a second, I can make this machine do what I want. And for a sizable minority of children, that's a really, as it was for me, I think, a transformative experience.